Hello everyone. In this lecture we are going to discuss about a concept of hydraulic gradient line and total energy line. To understand, let's take an example here. So this is an example of pipe flow where flow takes place from a high pressure tank to a low pressure tank. So we know that as soon as water enters the second tank, that is here, the total head remaining in the water will be equal to water level in this tank, in the second tank. Now it started from a higher head of this much. So in between, this energy is being lost in the process of flow. So we'll see how it is being lost, and to represent that graphically we'll use these concepts of hydraulic gradient line and total energy line. Now we can simply draw a line where it will be joining the two heads at the extremes, that means at the beginning and at the end of the pipe flow. So this will be approximately the energy line or total energy line, because if you measure the head at this point, you'll find that the head will be approximately this much. At a point downstream, the head will be lost because of friction and the head will only remain as a smaller value. But if we look closer, then it will not be exactly like this, because we have also learned about the minor losses, and the minor losses will be happening at, in this case, at the entry here. Therefore, as soon as the water enters this pipe, then some energy is already being lost in transition, and so that means if we use a manometer at this point, then this manometer will show us a head slightly below the total or the original head, and this is the loss because of the entry. Then when water is flowing inside the pipe, we know that it has some velocity, which was not the case inside the tank. Inside the tank, the velocity was 0, and inside this pipe there is a considerable amount of velocity. That means the total energy is not just pressure and datum, but now it is also pressure and datum plus velocity. So therefore, if we try to measure the piezometric head, suppose at this point, by installing a piezometer, which is just a small tube like this, then we'll see that the water level is rising up to some level, suppose this much. But this is only measuring the datum and the pressure head, which is Z plus P by rho G. The velocity head, which is V square by 2G, is cannot be measured using a piezometer, but it can be measured by using something called a pitot tube. So a pitot tube is, if you have a pipe like this, if flow is taking place in this direction, then a very small tube of L shape is inserted into the flow and then connected into the piezometer or manometer. So in that case, if originally water was lifted up to this level, now because of this L-shaped tube, the velocity will also be able to push that water a little bit further, and instead of rising up to this much level, it will rise now up to a higher level. So the amount by which this velocity is raising the water is equal to our v square by 2g, which is the velocity head. That means at every point we can either measure the piezometric head or we can also measure the total head. So if we keep measuring like this, the piezometric head and velocity head, we'll see that at this point the total head will be slightly less because of the loss at entry, and the piezometric head will be even lesser because we have subtracted the velocity head. And if you consider this point, then suppose total head is this much and velocity and piezometric head is this much, while this difference is the velocity head. Similarly, if you consider somewhere near the end, then also you'll see that this much will be the pressure head and this much will be the velocity head, the total head, and the difference is the velocity head. So that can be true for any point in between. So by joining these points where we measure only the piezometric head or where we measure the total head, we can draw two lines. This one line will be coming like this and meet the second water surface here, and another line will be slightly above this, and the amount by which this second line is above the first line is equal to the velocity head. Now this line above is called the total energy line, or TEL, and the line below, which is only representing the piezometric head, is called hydraulic gradient line, or HGL. Now let's revisit this again. You can see that as soon as the water enters the pipe, that means at this point, we have already lost some head, which is the entry loss, and hydraulic gradient line representing piezometric head is slightly below the total energy line, and at the end the total energy line will be slightly above the water surface, and that's because as soon as water enters this tank, whatever velocity head it had before entering will be lost in this mass of water and will be lost into the atmosphere by viscous dissipation in form of heat and sound and all those things that we have discussed earlier. So this is the basic concept of hydraulic gradient line and total energy line. And in between, we have assumed it to be a straight line. That means it decreases linearly, and that's because inside the pipe the loss of head is only because of friction, and because of friction we know that the equation is head loss is equal to FLV square by 2GD, and if we increase L as we move along the length of the pipe, L increases, and as L increases, since this head loss is directly proportional to L, therefore we can say that it will be decreasing linearly. Now let's take another example. Here we don't have a single pipe, but one pipe is starting from the tank, then there is a joint, then there is another pipe, and then the pipe has enlarged in diameter, and then it reaches the second tank. So in this case, the starting point will be the same. Some energy will be lost already. Then, so we'll start our total energy from this line. We cannot get this line because that entry loss is already there. No, and the hydraulic gradient line, which is showing the piezometric head, which is pressure plus datum head, will be slightly below it, and the difference between these two will be the velocity head. So if we want to draw these two lines, then we can start from here, and we know that it will be reaching about here, the total energy line, and whatever is the difference between the water surface will be the velocity head. But let's start drawing the hydraulic gradient line. So if this is the total energy line, the starting point of total energy line, somewhere around here we'll have the starting point of hydraulic gradient line, which is just P by rho g plus Z, and this total energy line is again P by rho g plus Z plus V square by 2g. So we'll start drawing here, and it will keep decreasing along the length of the pipe, and at this joint there will be some minor loss because it's suppose a not very well designed and rough kind of joint, so some energy will be lost here. So that we can show by this kind of a sudden drop in loss in head. Then again it will keep coming like this. Again at this contraction, this enlargement or expansion, some more head will be lost, and after that in this larger diameter pipe, since we know that FL V square by 2GD is the head loss, and if you consider L equal to 1, then it is inversely proportional to D, and therefore in this case the diameter has increased, and you can say that the head loss per unit length will also decrease. That means in this portion and in this portion the velocity was greater and the diameter is smaller, therefore the head was dropping at a faster rate. But in this larger pipe the velocity, the head will be lost in a slower rate, and therefore the slope of this line will be slightly flatter than the previous lines. So here it is dropping rapidly, but here this is dropping slightly slower. Now we can also draw the total energy line here. So total energy line will start at this point, and it will come parallel to the hydraulic gradient line. It's parallel because from here to here, within this length of this pipe, the velocity has not changed, and therefore velocity head at this point and velocity head at this point will be same, and that means that both these lines will come parallel to each other. Again, some loss will be there at this point. Again, it will come parallel to the other line, and then some loss will be here. And now you can notice something, that if I draw it like this difference between the hydraulic gradient line and the total energy line is smaller than the difference between the previous pipes. That's because in the previous pipes a greater portion of the energy was velocity head or velocity energy or kinetic energy, because the pipe diameter was less and therefore water was flowing faster. But in this larger pipe, water will be flowing at a slower rate and therefore velocity head will be a smaller value. And just like the previous case, at the end, whatever velocity head was remaining, this portion will be definitely be lost after entering this tank. So this is how we draw the total energy line and hydraulic gradient line. Now let's take another example like this. So again we have one pipe, a joint, another pipe slightly greater diameter, then a pipe which is moving upwards, then another horizontal pipe downward, another horizontal pipe, and exit. Now there are all these bends as well. So in these bends also we can expect some kind of head loss. So if you try to draw the hydraulic gradient line or total energy line, we'll start with the entry loss here, and the hydraulic gradient line will be coming like this. Then at this point some loss will take place and it will have a small drop and then again start coming. And if we consider that this pipe is slightly of greater diameter, then this portion of the line will be having slightly flatter slope, and it's difficult to show the head loss in this length of the pipe, and that's because we are drawing a 2D diagram. So if we are only concerned about the horizontal variation of head in the horizontal direction only, then we can simply come to this point. At this point the head loss will be because of this bend, this extra length of pipe, and this bend. So we can subtract a significant amount of head at within this small length. So again after that there will be this gradual loss over this length of pipe. Again at over this small length, very small length, loss due to this bend, loss due to this vertical pipe section, loss due to this bend will amount to a significant amount of loss. And again after that, at the end, over this length of pipe we'll have the remaining head lost. Now this is the hydraulic gradient line. So if we want to draw the total energy line, then we can simply draw it like this. And at the end, whatever was the velocity head, v square by 2g will be lost, and we are left with only this much energy, whereas we started from this much energy. So this is how we draw the hydraulic gradient lines and total energy line. Now if we want to describe what is a hydraulic gradient line, it is the line representing the piezometric head of flow, and the slope of the hydraulic gradient line is also the rate of change of head or piezometric head, and it's called the hydraulic gradient. The term gradient means slope, and therefore slope of the head HGL is called actually the hydraulic gradient. Now the slope of hydraulic gradient may be positive or negative. Now what does this mean? We have, in the previous example, we've seen that in this example as well as the example before that, we've seen that the lines are always coming down. That means the hydraulic gradient or the slope is always negative in this direction. But here we are saying that the slope of hydraulic gradient line may be positive or negative. It means the negative example we have already seen, but can it be positive? Let's look at this example. In this case, if you consider this pipe, the first pipe, hydraulic gradient line will be somewhere around here, while the total energy line will be about here. Now as soon as it enters this bigger cross section of pipe, then energy will be lost, and again it will flow like this. The energy loss will be like this, the total energy. But what about the piezometric head? In this case, since we are considering only horizontal pipe, the Z value is immaterial because the Z is going to be constant everywhere along this pipe. But the pressure difference, if we remember Bernoulli's equation, it said that P by rho G plus Z plus V square by 2G, if we put P1, Z1, V1 should be equal to P2 by rho G plus Z2 plus V2 square by 2G. Now Z1 and Z2 are ignored here because the pipe is horizontal already. Now we are left with P and V. If V is increasing, or sorry, if V is decreasing, then P must increase. And that's what is actually happening in this case, where in a larger diameter pipe, pressure will increase, but the velocity will decrease. And that means, although we are seeing that the total energy is obviously decreasing because it is being lost, but the hydraulic gradient line may not be falling like this. In some cases, it may rise up. Like this. And what does it mean? That it means that although the total energy is decreasing, at this point the pressure has actually increased, and although there is a negative pressure gradient in this case, or adverse pressure gradient, P2 is greater than P1, flow will still take place because it already had a high velocity. That is, the velocity, the kinetic energy will push it through this adverse pressure gradient, which is trying to make it flow in the reverse way. However, is it actually going to rise or is it actually going to fall? That will depend on the actual calculations. Sometimes for a small increase in diameter, the pressure will also be smaller because some loss will be there, and that loss will be shared by the velocity and the pressure, and therefore how much will be the actual pressure drop or increase will depend from problem to problem. So in this case we can expect that the pressure head at this point will be smaller than pressure at this point. Similarly, pressure at this point may be smaller than pressure at this point. So in that case, at these junctions, the hydraulic gradient line may have a positive slope, although the total energy line will always be having a negative slope. So let's draw the total energy line here, and the hydraulic gradient line will be somewhat like this. Here we have not done the proper calculations, so we do not exactly know if this slope will be negative or positive. But based on a hypothesis, we are saying that at this point the slope will be slightly positive, at this point it will be negative, and so on. We'll do some example later on to see how these things can be possible. So now we know that the line representing the total energy or total head is called the total energy line, and it's the sum of datum head, pressure head, and velocity head, and slope of energy line is always negative. Now hydraulic gradient in channel flow, if it's a channel, then we can say that the hydraulic gradient line coincides with the flow surface and the total energy line lies above the HGL or hydraulic gradient line. Now what does it mean? If we have a channel like this over which flow is taking place in this direction, so in this flow, if you take this cross section, the head, the piezometric head, which is supposed to be shown by the hydraulic gradient line, will be equal to datum head. So the datum is supposed somewhere around here, just an arbitrary horizontal surface. So this datum head plus the pressure head will be equal to the depth of flow in case of open channel flow, unlike pipe flow. So at this point the total the piezometric head will be equal to datum plus pressure head, and it will coincide with the flow surface or the open surface of water. Similarly, in this point, this cross section also, it will be datum head plus the pressure head. If the depth somehow increases here, then similarly pressure also increases and datum is this much. So at each point in an open channel flow, you can see that the piezometric head is actually equal to the height of the water surface, and therefore the hydraulic gradient line will be just the water surface, or it will coincide with the water surface or flow surface. But the total energy line will be slightly above it if the velocity is very high. Suppose it's a very fast flow, then the total energy line will be somewhere around here, which, and the difference represents v square by 2g, the velocity head. Or if the flow is very slow, in that case the line will be very close to the water surface. How much closer or how much higher this imaginary total energy line will be, you can get that directly by using a pitot tube, which is, as we have discussed, this kind of a glass tube of L shape. So if you insert this tube here in the flow, then we'll see that water has risen up to this much level. So if you insert another such tube here, then you'll see that it is rising up to this much level. And by joining the levels of different pitot tubes at different points, if you join all these levels, you'll get this total energy line. Actually, it will not be that case, because the velocity inside across this cross section is different. Velocity at this point will be different than velocity at this point and this point. But in an average sense, you should be able to get this total energy line using a pitot tube. So this is all about hydraulic gradient line and total energy line. I hope you have understood, and you can try to draw these lines for all the pipe flow problems that you can practice. So we'll do some problems in some of the live lecture sessions later on. Thank you.